All right, what's up, guys? So thank you, Ethan, for such a wonderful FEA session. It's very exciting. All right, so for those of you who have downloaded ANSYS, in order to actually access what I'm on here, this is like the starting page. You should just search for like Workbench. If you type in Workbench, it'll show up, and then you just press on that, and then it'll take you there. If you haven't downloaded ANSYS, I think the USF Gateway portal has that already available to you, so you can use that instead. So first of all, is everyone here? Good. Be in there? Want me to wait a little?
Yeah,
Okay, yeah.
Oh, and then can you put the, are you recording from your laptop?
Yeah, I think so.
Yeah. And you got it. Yes, no, it's good for it. Easy things. Right. You're. Yeah, you're just, we're just starting to advance this one. First should be here and it's any minute. On Monday, I asked, me when I told him he's to work 7. And then just later that day, I met up with you and this thing. Sorry, sorry, we'll be able to take on my bird. I think so. You're right. Are you? It's completely doing a little reading. Okay. I was showing. He's telling me. Wait, what are you guys making? It's just me making sense. It's kind of full. Yeah. Where you're saying they're already like. Money. I said, yeah. Because nothing. Yeah. No. You're coming. Oh, That is PR. Oh, is the USF like we add there too? Oh, did you already open? Did you open? This is like this just complete.
You guys good?
Yeah, I think we're ready to start.
Okay, cool. So once you're in this area, first of all, when people hear the words like ANSYS, they almost always immediately think of like a fluid simulation, but that's not always the case. There's actually a lot that you can do just under this like analysis systems tab. You can do so much. You can even do your own FEA like you did in SolidWorks, but you can use it with ANSYS instead. They have, FEA, they have stuff for like structural mechanics, stuff for electrical mechanics. So in our case, though, we're going to do a fluid simulation over the fuselage that you should have downloaded. So to do that, you're going to click on Fluid Flow Fluent, and you can drag that over, or you can just double click on it. And this box is going to show up. So this is pretty much outlining each step that we're going to take in order to first like import the geometry, and then creating the mesh, doing the setup, and then post-processing of the results. Okay. So once you have that, what we can do is we can right click on geometry. Don't double click on it, just right click on it. And you're going to see these three different features that you can select. So for now, we're going to just click new space claim geometry. And we'll just wait for that to load. My laptop takes some time, so bear with me. Space claim, yeah.
Everyone wants to get food, free food out there. Literally, this is loaded version.
So wait, you switch to form, put flow.
Fluent flow, yep. Fluid fluent flow.
What do you?
And then you right click on geometry and select space claim geometry. You guys good?
Yeah.
All right. So once you're in here, now we're just going to import the geometry. So we're going to click on File, Open, and just select the step file that you have, the fuselage fixed, and that should be the step file. Fuselage updated. Now, once this is imported, oh, it is. Gotcha. Okay. That's fine. Yeah, good. Good. You need to wait? Good. All right. So once you have the geometry imported, what we're going to do here is we're going to fix the geometry a little bit. And the good thing, the reason that why I went into space claim first is because this sort of CAD feature is really good in terms of repairing the geometry in the instance that there are any like very sharp curves or very like weird edges that are harder to find, which might mess up with the mesh later on down the line. So to do that, or in order to even determine if that's the case for your certain geometry, what you can do is you can right click on this solid and you can click check geometry. And when you do that, it's going to show you that, okay, it's going to give you some warnings. In this case, like an edge is inexact. And so you know that you have to do something to fix this, right? So what you can do is you can close it and you can go up here to the repair tab. Once you click that, you can click on this inexact edge and you can just click check. You don't have the repair tab?
Problems. Yeah, means this will be.
Oh, really?
Yeah.
Well, you can click inexact edge.
Oh, yeah, go to tools.
Yeah.
Pair body.
There you go. Yeah, that's fine.
Wait, I'll start check geometry.
After check geometry, in my case, I go to repair, but I think Ethan says you can go to tools.
Oh, that's 2025.
Okay, so yeah, you can just go to repair then. Yeah.
Yeah, so just close down. That just shows you that.
You got a nice.
You fine?
I don't.
Take a minute.
Well, no, I think it's saying that. Don't worry about this. I think that's bad. Yeah, I think it's fine. Uh-oh. Well, I put check down here, but some not down. I don't think we're. Or seven video, yeah, but nothing comes up. All right. Yeah.
Good, good. Okay, cool. So you're gonna do this for each thing that's here. You're gonna do it for inexact edges. You already did it. You're gonna do it for simplify as well. Just click the check mark, and same with small faces. And then what we can do is we can do the same thing. We can check geometry. And in this case, it says no geometry problems were found.
Please leave it. For one purpose. That's where it is. Right. No.
Questions? No? You guys good?
But it doesn't matter. My thing says none, or it says solid, doesn't.
It says none.
Yeah.
Can you rename it?
Oh.
Just out of curiosity.
Yeah.
So first of all, do you see like a cube here?
Yeah.
Okay, cool. Is this filled in like this side of the fuselage? Is that filled? Everything's orange. That's cool.
I think it's on. Yeah. Did you put it back there?
Oh.
Nah, mine's already found. It's ready for next time.
So it's orange if you click on solid, right?
It's I'm doing small. Oh, which one? The joke too. Okay, now mine is clear. Oh,
It's good.
yeah.
Okay. Just make sure when you right click and you check geometry that there's no problems.
Yeah.
Okay, cool. So once you're done with that step, we're pretty much done with this specifically. So you can click exit space claim, or you can just close out of it. And this will take you back to the workbench. And what I'm going to do is still in the geometry step. I'm going to right click again, and I'm going to go into design modeler. I'm going to click edit geometry in design modeler.
Sorry, you know, where you said design?
Yep.
Can you do it again? Sorry.
Yeah. So you're at the step?
Yeah.
Which part are you at? In the space claim?
Yeah. Yeah. It's all good to go from there.
Yeah.
And then we go to space.
No, you do all that in space claim. In space claim. Everything we just did was in space claim.
That's why
Gotcha, gotcha.
Where you get down, you pull the chair. Why don't I figure it out? I'll do this card, move this.
That's why I'm thinking. Was he good?
I'm waiting for Ethan. I'm waiting for Ethan. Are you good? Okay, cool. All right, so then once you're in Design Modeler, you can click on the import one. This is pretty much the geometry that we just messed with, and we're going to click generate, which is up here. And we're just going to wait for that to get imported. You can select import one and then generate. Mhm. All right. All right. So right now we have the actual solid body of the fuselage, but in our case, we're not concerned about the solid body, right? We're concerned about the fluid that's around the solid body. So the air, pretty much. That's what we're trying to model. And so right now, what we're going to do here is we're actually going to create the domain of the air that's around the fuselage. And we're going to pretty much subtract the entire volume of the fuselage from that domain. And that's what we're going to run the simulation on. So to do that, first thing to do is you can go over here and you can select the YZ plane. And then you can, from these two options, just click sketching. If you want to go normal to this plane, you can also hover over like this bottom right coordinate system. And if you see here, there's just like negative X direction. I'm just going to go there, click on that.
Oh,
Sketching is, yeah. So if you want to go normal to a certain plane, you can look at this like bottom right corner, and you can literally just select, in this case, I'm selecting the minus X direction, and it'll just take you normal to that. Good?
So the YZ.
Yes, the YZ plane. So when you're in modeling, there's like, they show you all these, just click on that. That's all you have to do. And then you can go to sketching. All right. So at this step, what I'm going to do is I'm going to select rectangle, and I'm just going to draw a rectangle around this entire fuselage. And I'm going to leave a little bit of space behind it as well, because maybe there's something in the wake that I want to model, you know. So once you have that, then we can go ahead and begin dimensioning. So you can click the dimensioning tab. And from here, you can click length/distance. So similar to SolidWorks, we're going to dimension the rectangle that we have. And you can click on the center line as well as the top line, and we can set that distance. In this case, do you guys have this like bottom left details view? Yeah. So you can click on the dimension there and you can adjust it. Here I'm going to select 0.8. This is all in meters, by the way. And I'm going to do the same thing for the center line to the bottom. So those done, I'm going to do something similar with the horizontal lengths. So I'm going to select this vertical line with the far right, and I'm going to select that as 1 meter. And then from that vertical line to the very end, I'm going to select that to be, say, 3.5.
length distance, right?
Yep.
So punto yung character one is a few. He was always without feeling. Oh no. I guess I think it was not.
No, no sé qué, resulta con la recta, los para mira, tengo que
You guys good?
Yeah.
So. I did that.
¿Y eso? Entonces, no sé qué es. Ah, mira, entonces la ahorita y tiene así. Sí, mira.
Yeah.
All right. So next step, we're gonna just extrude this out. So I'm gonna click extrude up here in the top left corner, right there. Gonna click extrude. And I want to capture this entire fuselage. So right now it's only 1 meter down in the details view, bottom left. I'm gonna change that to, let's say, 1.5 meters. The top left's over here. So extrude.
Look at the middle for the web thing.
Oh, it's on my right side.
Okay.
Yeah.
So once you have that down, you can click generate again. 1.5, yeah. And actually, yeah, so once you generate it, click on extrude one again. I forgot to do something there. So in the details view, at this operation, it says add material. I'm gonna change this to add frozen. This just doesn't merge the fuselage body with the current extruded feature that you're trying to make. So once you do that, go ahead and generate it again. And then it should be good to go. After the extrude, like after you extrude it. So click on extrude one. And then there's like the details view again. Just make sure that the operation is add frozen instead of add material. All right.
Says English.
Pero como
He's very easy.
Sorry, dude,
Hindi mo kasi mo sa palo distinto. Pero la misma.
Interesting.
Okay. It's super.
That shows up here. Interesting. Okay, this one changed. Yeah.
Oh, yeah.
Oops. Yes. Okay, so that works. This. So now you should be good. Yeah.
Thank you. So is your wing inside the straighten?
Yeah, right now the wing is inside. Yeah.
Try to use log method.
But not using sound could be.
Now if I play generating.
Oh, you have.
Inteligencia.
Oh, so.
All right, so next step. So now we have this overall volume as well as the solid fuselage body. So now what I'm going to do is I'm going to subtract the volume of the fuselage from the domain. To do that, up here I have a create tab, and there should be something called Boolean. So go to create and then Boolean, select that. And then again, in the bottom left, there's a details view. In the operation, you're going to change that from unite to subtract. And then these two different tabs are going to pop up. For target bodies, we're going to select the air. So I select the air from here. You could probably also select it clicking on it here. I'm going to click apply to that. And for the tool bodies, I'm going to select the fuselage. Click apply. And I'm going to generate that. And so now it gets cut out completely from the domain. At this point, you should only have one part, one body, which is just that air domain that we're talking about. All right. Yeah, what's up?
Can you make the box again?
Make the box again?
Yeah.
Oh my God, Ethan, what the hell? Just kidding. Okay. So do you have like the sketch or no? Like, do you actually, or I can like go through that? Okay. So what step are you on?
Body is prepared instead.
Okay, the body is prepared. Okay, so you're in design model, right?
Yeah.
Okay, cool. So click on the YZ plane, and there should be sketching next to this modeling tab. Good. So there's sketching next to the modeling tab. Just click on that, and you want to go normal to the YZ plane. So in order to do that, you can go to the bottom right, like you see the coordinate system at the bottom right.
Yeah.
We can hover over like a section of it. In this case, the -x direction, and you can just click on that arrow, and it'll take you normal. Yeah.
Okay, yeah, I got it.
And again, just make sure that in modeling you have the YZ plane selected. And when you go to sketching, you can click the rectangle and then literally just draw the rectangle around the fuselage. And to dimension it, you just click on dimensions, select length/distance. Okay. And then these dimensions, you can just select like each of these vertical lines, so the vertical line and the horizontal line, and then go to each of the edges of the rectangle. And in my case, I set the dimensions to be 0.8 meters for this horizontal to the top, 0.8 meters for the horizontal to the bottom, 1 meter for the leading edge of the fuselage to the front of the rectangle, and 3.5 meters for leading edge of the fuselage to the back. Yeah.
Oh, second. You're gonna take me go with the bottom. Oh, yeah.
L4, L1.
It was like, wait a minute. Yeah, on the side.
Bro,
Bro, this TV is actually way too small for the back row. What else? That's been good stuff. Yeah.
Most of the hard part. Ya me claro que no fue la puerta, el sector de educación de verdad. Puedes calcular la formación de mis switch o la cabeza del niño. Debería más de
All right. I'm gonna move on to the next step. So right now we have this domain that has the cutout of the volume. So we're pretty much done here. We can go to file, we can exit, or you could close design model, or you can just exit out and go back to the workbench. And once you're here, we can go ahead and edit the mesh. Right. Once you have this open, what you can do is you can click on this mesh, and you should see details of mesh at the bottom left. And we're going to change a couple of things here. Currently, it says the element size is 0.25 meters, which is a lot. And so we don't want to do that for the entire fluid domain. Mainly what we're curious about is refining the mesh around the actual curves of the fuselage, since that's where everything is happening. And then far upstream or away from that is going to be less refined, so more coarse.
It looks solid.
Looks solid, like there's no cutout anywhere.
No, there's a cutout, but it looks sort of block like a long scan.
Oh, yeah, that's fine. That's fine. That's fine. It's just the way that it displays it. I'm pretty sure there's a way to change it, but it's okay. It doesn't matter. You got it? Okay. All right. So yeah. So now once you are in the details of mesh, there's a sizing tab that I'm going to open up. And what we're going to change specifically is there's something called mesh defeaturing. This pretty much simplifies the geometry. In this case, I don't want to do that. I sort of want to, capture all the curves and everything like that. So I'm going to select this as no. And ensure that capture curvature is on. So yes, so anytime that there's a curve, this is going to refine the mesh around that curve. Just make sure that's a yes. And then capture proximity, we're going to turn that to yes as well. So anywhere that there's going to be an edge connected to another edge it's also going to refine around there. And so once you have those features, you can go ahead and click generate. Take some time. Once that's done, you should see your mesh. And you can see that closer to the actual fuselage, you can actually see that it is more refined, which is what we want, right? You want to have smaller elements there so that you can get more accurate results around that section, but then further upstream or far upstream, it's much coarser. It looks solid again. Go up here. So if I click shaded exterior, then it does that. You can click wireframe. Yeah. And it should change it there. All right. So that's a really quick and easy way to get a mesh that's, relatively refined in the areas that you want to see. One more thing that I'm going to do is add some name selection. So when I go to the setup, I want to make sure that what I'm setting as an inlet condition is actually at the inlet. So to do that, there are some options up here. In particular, I'm going to click face. So this pretty much just means if I go to select something at the actual geometry, it's going to select faces instead of the entire body. And I'm going to select the inlet to be essentially the face that's closest to the leading edge of the fuselage. And I'm going to right click on that face. When I right click on it, it's going to bring up all these options. I'm just going to say create name selection. And I'm going to rename it as inlet. Okay. And for the outlet, I'm going to do something similar. So outlet, create name selection, call that outlet. And then for the body that I actually initially built the rectangle off of, I'm going to select this and call this symmetry. So pretty much if I were to reflect the fuselage off of this face, it'll be symmetric, right? So along that face, I'm going to call this symmetry. And for all the other faces, I'm just going to name those free stream. I'll click OK.
When you selected symmetry, do you select the face or the body of the fuselage?
Just the face, yeah. Free stream. Okay. All right, and then that's it for the mesh. Actually, before you close out, if you actually want to understand what like the number of elements are in the mesh, go back up here and just select body. So what you can do is you can select this entire volume. And there should be something here. If there isn't, there's something down here called like body selected. You can just click on that and it'll show up. And if you select that body, it'll show you like all the elements that we have. So in this case, we have almost 1 million cells. Yeah. So ANSYS is like kind of has a limitation for the student version where you can't go above 1 million. If it does, then it literally just doesn't run the simulation. So you always want to make sure you're below that. In this case, we're like just there. Right? Yeah, I know. Seriously, if you didn't do that, this would not work. But,
I was gonna ask about that. Why not do the whole thing?
yeah, exactly. Yeah, you want to save the element size. And in this case, you know that the body is symmetric, right?
Right.
So you don't really need it. Like you can entire simulation just based on this, and then say like multiply by 2 if you're trying to find like lift or drag or whatever. So yeah, you have to think that way if you want to be efficient.
But it will make it more precise.
Maybe. I'm trying to think like if you had the entire full body, of course that would be good, but you have to make like certain assumptions that maybe the other side of the aircraft isn't going to have as much of an effect on the side, like this side, for example. So you sort of have to make assumptions like that, and they tend to be fine, you know. Yeah, so cool. We're done with that. You can go ahead and exit out of that. And then if you see this like little lightning bolt next to the mesh, you can right click on it and just click update.
Importante que el día
All right, once you have that updated, you can go into the actual setup now. So again, you can click edit at the setup, wait for that to open up. It's going to pop up with this menu first. Obviously, we're dealing with a 3D simulation. If you had maybe just a slice of an airfoil, for example, you could run a 2D simulation on it and just, you know, observe the effects over that airfoil. But in this case, it already knows that it's 3D based on our geometry, so it has that selected. What I'm going to do is select double precision for the solver options. And in terms of solver processes, in my case, I have 4 logical processors on my laptop. It's going to vary per machine. So just make sure that that's accurate for you. Yeah. At least one. I think I actually have 6. So don't select like the max number of processors that your laptop has. Maybe go like a couple less. Anyway. Yeah, you can start it. Yeah, so if you go to like device manager, you should be able to see like processors down here. And in my case, I have 6, but I selected like 2 less than that. I have 4. So typically you want to go less. Yeah, I think 4 is probably good for most people. Yeah, the more processors they have, the more efficient it's going to be.
Swear to God, it's scary.
And again, don't select the max number of processors that you have.
16?
Yeah.
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 Yes, sir.
Is it so good? Does it like?
What's up?
Is it so good like setup?
We're about to do like run the simulation. Yeah.
Why would one? They're probably. Put 5,000. Yeah.
All right. You guys good? Giving up? Yeah, it's just loading. Just loading.
I said, what's over? It's. Yeah, probably. No, we want it. Oh, so you guys live so. Those things are lower on. And then are you trying to get the lessons? Yeah, he mentioned his Memorize. Yes. That's good. Oh, no, we don't want to. Yeah. We're supposed to get frozen. Okay, delete completely. It's solid. And mine, finish with one, right there. And then selections.
All right. I'm just gonna continue. That's okay. Good. Okay. So what I'm gonna do is I'm gonna show the actual mesh. So I can select edges there and display. And here's the actual sort of wire mesh that we made. Typically, the first thing you're going to do is decide which type of solver you want. If you're dealing with like super high speed flow, you're going to choose density based. It just optimizes for like a very compressible flow. In this case, we're not like dealing with any kind of supersonic vehicle. So we're just going to stick with pressure based. And whether the simulation is steady or transient, in our case, it's just steady. Nothing is really changing with time. So we're going to keep that. There's also all these models that you can select. So if you want to include like viscosity, there's that model, you can double click on it. And there's all of these different like viscosity models that you can select. I'm just going to keep it as the default K omega. And yeah, so there's all of that kind of stuff you can look at. Additionally, for the materials, if you look at materials, there's the actual fluid. So in our case, we're dealing with air. It should already be imported as air, but if you double click on that, you can see like, okay, the density of air is there, it's constant. You can also change it to like ideal gas if you want to. I'm going to keep it as constant though for this simulation. And if you want to change it, there's also the database there. So you can open that and it has all those materials or all those fluids you can select from. All right.
Is there water then?
What's up?
Does it
Water?
have water?
Yeah, there's water. Okay. All right, and then next up would be the boundary conditions. So like I said, we have the inlet, right? But we want to select what the velocity of the inlet is going to be. So this is going to be the velocity of air actually coming towards the fuselage. I'm going to change this to, you know, 20 meters per second. I don't know how fast your 20 is good. Okay. And I'm going to close that. And then I'm gonna go to the outlet. And I'm gonna go to pressure. This I'm not gonna change, but I'm just gonna show you that it says gauge pressure here, which is perfectly reasonable. We're just gonna assume that the outlet is far enough beyond the fuselage that it's just gonna be atmospheric. So we're gonna leave that as it is. And one other thing we're gonna do is right now it says free stream is a wall, but if you're familiar with like viscous flow, there's something called the no slip condition, which implies that at a wall there's no velocity. But in our case, free stream obviously is going to have just the same velocity as the inlet. So what I'm going to do is I'm going to double click on free stream, and I'm going to change this wall motion to moving wall, and I'm going to select the same speed, 20 meters per second. I also have to specify the direction. So in this case, the direction, if you look at the coordinate system there, is going to be in the minus z direction. So turn that to x equals 0 and z is -1. And I'm going to apply that. All right. And we're pretty much finished with that section. Then we can actually go to the solution. There's a bunch of like different stuff you could do with the methods. This can all be left as a default option. Pretty much if you were to change it, it would maybe be for like a very particular reason. Maybe you want to get a little more precision in one area over another. So in that case, you would maybe change something. But for now, we'll keep it as it is. And then report definitions. This is where you can actually calculate like the lift and drag components. So if you go to force report, there's something called drag. You can select that. In this case, I'm going to rename it as drag, and I'm going to select drag force. And then for the zones, I'm going to select wall solid. This essentially corresponds to the surface of the fuselage. So I'm calculating the drag of the fuselage. And I'm going to click print to console. And again, which direction is drag going to be acting in? It'll be acting in the minus z direction. So I'm going to adjust that, -1. And hit apply, or okay. And same idea for force as well. So, or lift, sorry. So I'll select lifts, change this to lifts, select the force. And this is already acting in the Y direction, so I don't have to change anything there. I'll click print to console and solid wall. Okay. Close. All right. And then we're going to actually initialize. So there's something called standard initialization and hybrid initialization. Hybrid is fine for this reason. I'll just click initialize there. This is essentially setting up the initial values of the boundaries that you have selected. And we'll wait for that to run. Once that's done, we can actually go to run the calculation. So time step method, I'm going to say user specified. And number of iterations. This is a numerical solver. So if you have a larger number of iterations, then it's more likely that the solver itself will converge to a value, which just implies that it's going to be more accurate. So in this case, I'll just say 70 iterations. Obviously, if you increase it to like even more, it's going to take a little longer to run and to finish. So you have to keep that in mind. And once that's done, I'll click calculate. We'll wait for that to run. All right, so when you're running the actual calculation, it's going to pop up with a couple of graphs, specifically the scaled residuals. So this is what I'm saying I want to converge. So if you find that these lines are like exponentially increasing, then that's like a bad sign. That means that your simulation isn't doing well and you should stop and maybe change something. But otherwise, as your iterations continue to increase, you should see these like steadily decreasing and ultimately converging to a single value. Similarly with the drag and the lift plots, you might see them like increasing substantially per iteration, but then over time, as you reach the end of the actual calculation, it'll tend to reach some steady state value. And we'll just wait for that.
Where's the drag in this? Is that on CD or?
This is just drag force, so like the actual force. It would be useful to do that if you were dealing with like just the airfoil.
Yeah.
But because you're also considering the fuselage, it's gonna like mess with those results. Yeah, in that case, it's more appropriate to look at the total drag or total lift. Yeah,
How fast did you cut that flow?
20 meters per second. It's like 40,
Oh, it's like 40.
something like that. Yeah.
There's 5,000. There's 4. It's 23. 38.
It's 45 miles per hour.
So why does it like lines up from why they have like below area?
Yeah, so when you first begin the calculation, you're dealing with a numerical solver. So it's going to take some initial guess of what the lift could be. And it's going to plug that into like a calculation. And it's going to spit out some other value. And then for the next iteration, it uses that new value for another. Yeah, and it's going to continue that process per iteration. As it does that, it tends to converge over time. That's why you're seeing like as the iterations increase, it's like reaching the steady state value. That implies that like it's no longer like optimizing for anything. It's like it's finished, right?
Lo que te salía todo así.
So how does it go? It's like approaching more than it's like accurate value.
So based on the residuals, this is just an indication of like how much more did it change from the previous iteration. So that's why like you should see it decreasing, right? Yeah, exactly. It's like barely doing any change per iteration now. That just implies that it's now reaching this like steady value. Yeah, comp methods exactly.
Like a
What's that? Yeah, new horizon. Yeah, it's very similar. It's like you're using the same or calculator value that you got previously in your yeah. It's not using Newton Raphson specifically, but it's like a similar idea.
Okay.
Like different kinds of models use different numerical methods.
like differential.
Yeah. You know the Navier-Stokes equation?
You can that you need if I try and guess it one thing.
Yeah. Similar. You know of like Navier-Stokes? Okay, well, have you taken fluid systems or? Okay, so you'll learn about it probably a little bit, but that's like a very large, crazy like differential equation. It's like nonlinear, and it's used to describe like how fluid moves under different forces. So that's the like main thing that a lot of these simulations use is they're trying to solve Navier-Stokes. Yeah, it is. Yeah. How much does your thing weigh? Just out of curiosity.
Oh, you never.
Oh, you haven't built it. How much you expect it?
Yeah, the sun was still involved.
Your target.
11 kilos.
We could get.
Then I'll done made of the geometry, right? Not the material. Okay.
Yeah, exactly. Yeah, because well, the material is the air, right? So like I showed you, you could like change that specifically, but we don't care about the airfoil itself, right? We're not concerned about. Yeah, like you're only concerned about the surfaces or the surface of the airfoil. Yeah, so you don't have to specify like aluminum or anything. The fluid doesn't care about that, right? Yeah. Yeah. So if it weighs like 22 kilograms, if you look at the lift plot, it shows that it's converged at a value around like 55, which I don't know what 55 newtons is in kilos, but I think that's more. I think it's more. So you should see lift. Congratulations. Yeah, you should fly. You should. All right. And then now that that's done, we can close out of that. You guys good? Questions?
Oh, that's still live.
Yeah, this is a lift. And you also have the drag as well. So drag reached a value around like three newtons, yeah, around that.
I mean, does it flash?
Yeah, it depends on the weight of the. Yeah. Is 11 kilos 100 pounds? Oh yeah. Well, 11 kilos. 11 kilograms, right? Yeah. Yeah, you're right. I guess in this case it would not fly. 100 newtons, yeah. So in this case it would not fly. Sorry. But keep in mind, this is 1/2 of the fuselage. So you just multiply this by 2. And yeah, it'll be stationary in the air. It won't be rising or anything. Right.
How people.
Right, so, yeah. I just barely get a pen.
A pen as well as chalk too.
Yes, that's right.
Yes.
Oh.
I mean, no, it may play more, but I don't think it's playing. I never feel like it's
Yes. Is it, you know, if it's lighter?
I don't know.
I mean, it may fly if you have an engine. Like,
I guess this. So I did.
and leave.
Es que siempre hacer un glider que hace que de repente inicialmente tú
It's just like, I can have to. Well, but the culture usually. You never get it all down to the value of the machine, or even some weird, like, in the other ones, it's something for. Yeah. Oh, my goodness.
So I sort of speed ran it because I realized we're running out of time. But pretty much in the next step was like post-processing. You can do a lot of different things. Specifically, like these are the streamlines. So what is the fluid actually doing as it's going over the fuselage? You can kind of see like, okay, it's moving around the airfoil at a certain point. And you can also model like contours. So in this case, I modeled the pressure contour, specifically around the airfoil. And you can see that we have low pressure zone above the airfoil and high pressure zone below. So this is actually what's like producing the lift, right? And also there's a very sharp region, which is like very high in pressure. That's the stagnation pressure pretty much. So yeah, and you can do a lot of different stuff there. You want to change the, yeah, that's creating lift. Yeah, exactly. You can also look at the velocity. So changes to velocity by it. So you see that the velocity is traveling faster over the top portion of the airfoil compared to the bottom. And so that's like following Bernoulli's principle. Yeah. And then if you look close enough, at the very surface, there's what you see as like the no slip condition. So because we're looking at like a viscous flow simulation, because you're considering friction, if you're ever encountering a surface, you'll have zero velocity there. So that's what you find at the surface of that airfoil. Yeah. If you increase the refinement of the mesh, this would look a lot cleaner. This is velocity. It's increasing above the airfoil.
Red is more.
Yeah, yeah. Yep. If you look at pressure, you could do that. Pressure apply. And so there's lower pressure up here, higher pressure. Yeah.
We can hold it.
Yeah, good. And you always want to like compare it with NACA as well. So
True.
see if the results are accurate. So NACA was like, it was previously what NASA was. They did a lot of experiments over airfoils and they like documented it and provided it for the people. So like you could go online and look at what the lift would be at a certain angle of attack for one airfoil geometry.
It's so
Yeah.
for making air.
Yeah. The angle of attack. I mean, I didn't change the angle of attack. It's just like straight on. It's just 0.
Yeah, we're going to stay in power. Something like so we want to stay in power. Oh, that's pretty.
Yeah.
Wait. So we say, what are these lines? Up there.
That's the streamlines.
Well, it's a streamline. It's record.
Yeah.
Wow,
Streamlines of velocity.
that is so cool. So this is the streamlines that this airfoil makes.
Yeah.
Yeah, this one will work. Or we think it will.
Yeah. Yeah, it should work.
Do you have any like design recommendation? Anything you think that would make it better?
Well, you said it's just gliding.
Well, there's gonna be a motor back here pushing,
Okay, there's
but
another.
then also, oh yeah, I actually brought this up to you, but
Yeah, yeah.
there's like 2 rods sticking out with motors.
Right.
So
Right.
it's definitely gonna influence like ruin the streamlines for sure.
Yeah, yeah. Are those motors specifically just to like increase angle of attack or something? Or oh, it's like a VTOL. Oh, okay. Oh, cool.
And they don't. Those VTOL motors, they just they don't.
Okay. So once you're like in the air, when you're in the air and like you have the back motor that's turned on and that's going forward as well, are you gonna turn off those vertical? Okay, good. Yeah, yeah.
It's like the minute max getting up.
Yeah.
So once it's in forward flight, doesn't mean it's off.
Do you have any kind of like stabilizers? I don't remember. Do you?
Yeah. We haven't been designing them yet. We just have one. Run, and then on the V tail, it's gonna be elevators.
Okay.
Okay,
cool.
one bottom.
Oh, okay, cool. This is like a fan.
The problem, like, do you think that like moving them far out, that's gonna be
Well,
you move like farther out those VTOL motors are, like it would be for a lift, do you think?
Yeah. Where like effectively would those motors be if you were to look at it from the top down?
Like right about there.
I'll say you want them closer to the base, but we do have, they're like 22-inch cross. So
Yeah.
it's gonna have to clear by a little bit more. I know you want to do like a wingtip stall back there, like almost a minute. It's better
Yeah, it would
Better
be.
to install near the base and installing near the tips, depending on where your control switches are.
Yeah, I would say it would probably be better if it was closer to the body.
One thing you can do,
It's a flap, right? Right now. That's on the end.
you don't have to put flaps on. We can put flaps on if we need to, but since we're not landing eventually, you don't need flaps. Flaps are for
So
takeoff.
you just have an aileron. Aileron is supposed to be here.
Anyway, it could be the full wing, it could be the wingtips, it could be near the base. Depends on what type of students. So we're gonna get into in the summer. We could also raise the actual, do two things. We can raise those carbon rods with props above the aircraft, so they can be a little closer if we need to. Or we can flip upside down.
Oh, above.
We flip upside down because it'll be so close to the base is flat. Next to it. It's like also on the bottom we have like.
Oh, so you can just mount it to the fuselage and stuff. Maybe on the wings.
So do the wings, so you can do it on top and raise it above. So if you do the fuselage, we can or we can put it on the bottom. Same thing. We just need to figure out like big skins.
Yeah, that probably help. I think if you put the rods instead of putting them on the wing, you put them on the fuselage. Like if
The rods that are holding the.
yeah, the rods that are on the motor. You think
Yeah.
it'd be better to mount them this way or not this way?
I know they're developing this.
Because the motor is still gonna be like
Okay, yeah, if the motor length is the same, then yeah, it's better to be closer at the center, right?
close to the center.
Yeah, I think it's easier that way to like actually turn, like it's not gonna
True.
take as much power from the motors if you're trying to do that. How are you controlling, what's your control system? Like,
Aileron.
yeah, like how do you control the ailerons?
Like the actual.
Oh, is it controlled? With the controller?
Yeah.
Okay.
It also be alright.
Okay,
Those gonna be two flying. Flying.
But
It's
yeah,
pretty
we got or manual control.
yeah, that's a good idea.
Yeah.
It's gonna be a scary first flight.
Just bring out maybe make two of them or something.
We're gonna not work with mass stems for the Jetson and all the non-technical components of camera and stuff.
Yeah,
I don't want to.
maybe don't fly the Jetson first flight.
The batteries are free, so we can just still explode next
Yeah, the battery, you have batteries.
You're using LiPo batteries?
Yes.
We're making it really janky setup. So I got donated 6 4 batteries. So where the motor's hooked out, the amperage on it, we're gonna do 4 cells and payloads from 12S. It's like a 12S GP.
The capacity.
Yes. I think 180 kilowatt hours. You have, I think they're 8,000 a piece.
Jesus Christ, dude, that's insane.
Yeah. So flight time should be an hour. If you don't explode. Because we're pushing power is good. We're also pushing like close to 150 to 200 amps.
So it's a big bird.
Why are you, why is the flight time so long?
There's competition that you fly. But the long-term goal of this is really work on quad motors. You know, if you ever get the opportunity, I'd love to put because you can take flight time.
Like to replace the motors?
Yeah. So like for the pusher motor, like
Okay.
a gallon of gas and like a small V5 engine, you can get maybe 68 hours of flight time. Off of the gas.
Sounds nice.
So that's why those quads, like they're like 9 kilos per motor. So
That is insane.
I was able to mesh my box, but then it wouldn't get the setup.
When you get to set up,
I don't know.
was there any error with the mesh?
Oh, they were there.
That's probably why.
what's
So 55 newtons on like one side. So if you double it, then it's like 110. Yeah.
does that tail give us anything?
Uh,
Is it better to hand calculate the tail to figure out your lift coefficient?
I would, is it the same? The same?
No, it's not the sun. I picked the tail and act it.
I think but we have this yeah. Big over we have the screws.
So you could like easily determine it. If you know that the lift, if it's straight on, is 55 newtons, then you just take the normal component of that based on the angle that this is like oriented.
Oh, it's I don't know if he changed it, but when I did it, I think it was like between 110 and it's all bigger than 90. I think it's 110 degrees between these two.
Okay.
So from there it probably
Yeah. So we just need to.
55.
Okay. Yeah. So you just need to take the normal component of that based on the value that you've calculated from just the straight on. Yeah. Exactly. Yeah. So it should be easy.
But why is it?
I'm sure there's a way to. It's just I can change the position of the plane,
Yeah, that'd be.
but it wouldn't be like oriented at an angle. Right? It would be. Well, I guess it's still what you're concerned with.
Done. Did you give your got the file and a Discord too?
The what?
Like this file and the Discord?
Oh,
That's
sure.
possible.
I think so.
Okay. Yeah. Oh, there it goes. Nice.
Yeah. So this is like not oriented with the.
So you're saying this isn't accurate, or
Let's see.
I mean, does it need to be? Yeah, thank you guys all for coming. Appreciate you guys. I hope you're able to learn something. We'll have the recording in case you need to check back on it. If you have any questions, feel free to reach out to me or Maj. We'll be happy to help. Yeah, we'll be uploading the recording to the Discord. I'll probably be like a Google Drive link or something. Or I'll find something to upload it to. They'll be
I'll
able
have to spend some time to determine how to like find the actual value there.
Oh, yeah. Taking the difference. The lift on it from that.
Yeah. Yeah. That would be like the simplest way, I think. And if you want to validate it with the simulation, you can do that as well.
I graduated. I have one more time.
Okay.
I graduated. Yeah, next week.
It's that like computational component.